Hello folks and welcome. My name is Matt Adams. I'm the Vice President of Geoscience and Subsurface here at ShearPrac. This is a presentation on teaching an old dogma new tricks. It's a quirky play on words, but what we're going to do is we will look at how laboratory experiments done at the University of Toronto integrate with the field and how they can yield your company P10 production results. Normally this presentation I co-author with Professor Giovanni Griselli, who's the chair of fundamental rock physics at the University of Toronto. Giovanni is not available here for this filming, but I'm going to try my best to carry you through. When we started this experiment, we went through and some of the results that were yielded in experiments at the University of Toronto didn't yield what the books would tell us. So what we did is mined back through, and a good literature research back check is always prudent. So what we did here is we went back to the fundamentals of rock physics, and you may recognize the name of Marion King Hubbert. Marion King Hubbert in 1955 published a paper when he was at Shell as an engineer on peak oil theory. Peak oil theory was the prediction that we would run out of conventional resources in the year 2000. Hubbert then furthered his research with Shell and went into rock mechanics. He built simple biaxial tests in two platens where he would pour a gelatin slurry, inject plaster of Paris, and under these load conditions mine back the gelatin and see how the plaster actually formed. Now what's critical for this is I just went through his hypothesis and theory, and everyone is familiar with his final output, which is the fracture will propagate against least principal stress. What's interesting, if you look back in this paper in 1957, there are very interesting tests. Test 10 in particular was where they stratified the gelatin prior to injection. And when we talk about unconventional resource development, we're talking about shale, siltstones, low energy deposits of sediments which have high layered anisotropy. This was actually mimicked in Hubbert's test number 10, and you can see the fractures actually propagate along these bedding planes. What we're going to do is we're going to now take Hubbert's theory from 70 years ago, 1957, and we're going to go under new laboratory techniques, the best we could procure in the world, and we're going to replicate real resource rock, real reservoir rock under real reservoir conditions, and we're going to simulate a open hole single stage slick water frac, and we're going to see the results. Then what we're going to do is we're going to move forward and see how we can take those results, apply them to the field with a new open mindset, and see if they actually yield better production. So the dogma does run deep, and this comes down to the initial play on words of the title of the slide. When we look at production, all production engineers will explain to you that this is semi-hyperbolic decline. So you start off with hyperbolic decline, you get into an exponential tail. This is an example here of the Montney Formation, and you can see over time, you can see this does display the same production profile. You'll have different declines, different B factors when you get into different formations, different benches, and different locales, but all of them do behave in this similar profile production. This mathematically is best explained if you come down to the trilinear flow model. And this trilinear flow model is very simply broken down into three components, trilinear. So the first is the large bi-wing fracs, the second is the natural fractures within the reservoir, and the third is the matrix of the actual reservoir itself. Combined on those three allow for us to start off hard, decline in the middle, and end up with matrix-dominated flow over 50 years of the life of a well. This does permeate into rate transient analysis modeling, where if we cannot get a proper production match, we can generate an enhanced stimulated region. This enhanced stimulated region in rate transient analysis modeling is simply more permeability, natural fractures within the reservoir. If we look over into hydraulic fracture modeling, we can look here how there's been permeations of fracture modeling done in industry. We started off with a simple bi-wing fracture model. Simple bi-wing fracture model simply states Hubbert's principal stress methodology, that it's going perpendicular to least principal stress. Because this ran into challenges in industry when they tried to production match, there were attempts made in 3D modeling for dendritic fractures. Consider these tree roots or lightning bolts. Dendritic fracture is the proper word. And this was a better attempt to try and production match when we got into this. Ultimately, when we overlay ant tracking, when we overlay fracture networks, when we really let the fracture run rampant with no constraint on principal stress, we'll end up with a fracture model like this, which was done in Eclipse, which is a Schlumberger product. Fundamentally, you'll note, none of these fractures allow us to mimic Hubbard's stratified gelatin test, which did show bedding plane parting. So if I move to the next slide. Moving to the next slide, what we're going to do is we're going to take a sample of core, full diameter core in the Montney Formation. This is located in the Western Canadian Sedimentary Basin. And we know, based on a 1D mechanical earth model done on 1,100 wells, that we're in a strike-slip regime. And this was published in 2019 for reference under myself and Dr. Hani Abdul. And you can see here that general industry consensus is that we're going to drill parallel to the trend of the Rocky Mountains. This is under Hubbard's principal stress model, and it carries true. And according to Hubbard, if I take my principal stress regimes as defined by my 1D mechanical earth model, I should have a propagation of fractures which goes perpendicular to the smallest value, which is my least principal stress. It's the smallest one of the principal stresses. The overburden principal stress is simply calculated by the density of the rock pushing down, and the maximum principal stress is the force of the Rocky Mountains. So we'll call that Rock Mechanics 101. Now, if we take our 1D mechanical earth model and we take real reservoir rock, which was collected by full diameter core, and we're going to apply this to our true polyaxial system at the University of Toronto. This machine here, for scale, if I was to stand up here, I would be about this tall, and this machine, when procured, was $31 million, built in the late 90s. This was done for seismicity, tremors, earthquake, and volcanology. What this machine has the capability to do, and it's the only one in the world, it has 6 independent axes. So you're not just pushing from one side, you're pushing from dual sides, and we have enough force in the overburden direction to exhibit 1 gigapascal of force. That's equal to 40 kilometers depth. So we can gladly make diamonds in this machine. We're only going to bring this down to about 2,000 meters depth where the core was recovered from. As I move forward in the results of the experiment, once we take our cube, machined cube, put it in our true triaxial load cell, inject slick water frac fluid, and we want to mimic and see what an actual fracture stage looks like. You can see here we have LVDT sensors on this. So this is our initial static cube. You can see I've noted an acoustic emission event here. I failed to mention that this cube has 16 acoustic emission sensors wrapped all around it. So we know the energy going in. We have the acoustic emission sensors coming out. We want to hear for seismic, microseismic events. We did see an acoustic emission event here when it initially broke, and then you can see the different axes here. So ultimately, what we're showing here is there is a residual opening, and we can measure which direction the residual opening is going, if it's in the direction of least principal stress, or if it's in the direction of vertical bedding plane parting. These dots here actually signify what the actual pressure response was when we fractured this cube in experiments. This test was done 11 times, and when we did this, we could not get it to replicate the textbook of going against primarily least principal stress. We keep coming up against the challenge that bedding planes want to part. They have lower tensile strength, and we see this in all shales. Even if you go to a quarry which mines flagstone, They cleave along the bedding plane parting to make nice, thin, laminated shale flagstones for your garden. So you can see here, the induced fracture planes actually went parallel to sigma 2, which should be a real head scratcher because we know the forces applied within this machine. When we look closer at the hydraulic response during this fracture stage, you can see there are perturbations or a comb-like structure. We know where the acoustic emissions happen, so we can zero in on the cube and see exactly where what happened for each signature which happened in the rock. You can see here you have a very slow recovery, a large a fracture here which shows shear characteristics, and that's seen in the pressure response. We see the opposite here. We see a much steeper, which would indicate a different fracture response. Shearfrac, as a company, what we do is in the field, we use high resolution pressure sensors on your well. It's a passive monitoring, very affordable. And we're going to use a high resolution, which I would equate to a Nintendo 64 versus what industry uses, which is an Atari. So we're talking 12-bit versus 24-bit. That's the resolution we see. Knowing this, we can integrate these recoveries during the pressure wave when you frac, and we can break these down into different fracture complexity. We can tell the complexity of a frac. And the only way for a pressure to drop when you're fracking in a closed system is to open up a little bit more of the system. So each of these tooths in the comb is a new fracture opening. The rate of recovery, we can tell the style of frac and break it out. So we know how complex your fracture is. This is done in real time. And if we make changes at the surface, dynamic changes, we can observe them within the time they're pumped to make real-time active decisions in your frac to increase complexity. If we back up and we want to truth test ourselves, what I'll show you here is what the actual result is of the stimulated rock volume that we generated at the University of Toronto. This work was done by, I need to give credit to Dr. Ali Abdulaziz, who most of his PhD research under Professor Gurselli focused on this work. This cube shows that you can see, here's the borehole. This is 8 centimeters to scale. Here's the borehole. This is a natural fracture which exists here. We have some bi-wing fractures, or what we would call the dogma of thinking, bi-wing fractures. And then you can see the amount of bedding plane parting. I want to show for comparison what Hubbard's 1957 model looked like in plaster and gelatin versus what new high definition lab resolution response can get. We've then further taken this and we've generated this in a model which can be held in your hand. This is the full 3D cube of what was generated, and the resolution of this image right here is 20 gigabytes. So that's the resolution is half the size of a human hair within that. And that was done by machining through 50 microns at a time, imaging this with UV dye. So we get this beautiful image of what a fracture looks like, and now you can actually take it and you can hold a frac in your hand for the first time. So if we look at the results of this, we now look how rock fabric actually is a very integral and important part of the fracture geometry of the stimulated rock volume. This is critical because if I look at the fracture class volume, which is the total stimulated rock volume, I want to break this out into bedding plane parting, the bi-wing fractures, and the natural fractures within the rock. You can see if I look up, the majority is bedding plane parting at 61%, but the combined of natural fractures and bedding plane parting is almost 90%, with only 11% left for the bi-wing fractures. If we think back to the first slide we showed, the bi-wing fractures are what all models show. My comment was, current reservoir modeling can do this, it's challenged to do this. And in a layered anisotropic rock, I question the possibilities which you could achieve if you open up your mind of maybe that's a possibility in layered rock. So bedding plane parting in this experiment seems to be the primary stimulated rock volume. Additionally to that, if we look at the fracture aperture, because we have such a high resolution of this cube, we can measure the aperture of each classification of fractures. We can break these out and you can see the aperture of each, but the key to this portion of the slide pack is the aperture. The cube of the aperture is the permeability. And just think about that. The cube of the aperture is the permeability. So if I cube this value, it's going to be higher than this value. So the largest aperture is actually the bi-wing fracs, which also has the highest permeability. One limitation of this test is we were not allowed to pump proppant in a $30 million machine at those pressures at surface. So we have to infer, based on the size of the aperture generated, we infer that proppant could transport along the bedding plane and it would be propped open for flow. Here's our actual fluid pressure response, and you can see again on this what we see in a typical well. We have typical breakdown in the Montney Formation, which is 50 MPa, and you can see along this well bore these perturbations, which are volumes opening up, which are fractures. You have a tank, you increase your pumping pressure, pressure increases, you open up a new little portion of the tank, drops. As that recovers, shear frac goes through with detailed AI, ML, machine learning, frequency analytics, and we'll go through and actually understand how to make this more complex by making suggestions to your real-time pumping schedule, otherwise through proppant loading, viscosity, or rate changes. We do that in real time, as small as 1 barrel per minute, and we've seen real results. Over the whole lifetime of a well, ShearFrac is the only company who actually holds patents and does focus on this portion of the pumping job. The rest of it, when you talk about pressure transient analysis, rate transient analysis, flowback, ISIP defits, you can do a PhD on that, but ShearFrac is the only one analyzing that portion of the flow regime or the pressure regime. So the question I get asked is, well, Matt, Hubbard showed us that it wants to break against least principal stress. So this is a textbook I bought, Zhang 2020, Applied Petroleum Geomechanics, and this is probably the best quote I got out of it, which was fracture initiation and propagation is dependent on the in situ state of stress and the tensile strength of the rock. This part being the most important, the tensile strength of the rock. Under Hubbard's model, you can see here, I've put in what we showed initially for what the principal stresses were and their direction under a strike-slip regime. You can see here the least principal stress, 43, and Hubbard's model wants to fracture against this way. If we go back to the lab and take Brazilian disc tests parallel and perpendicular to the bedding plane orientation, you can see here is actual lab results, averages, which show what the difference is in perpendicular and parallel to the bedding plane. I like to think about it tearing a phone book like this versus opening the pages within a phone book. You can see the difference is 10 MPa. So if we take this along with Zhang 2020's basic math, we will add the principal stress plus the tensile strength of the rock in that orientation, 14, 14, 43, 43, 63, 43. You can see now our smallest summation of numbers actually becomes against the vertical stress in this rock itself. So under this stress regime, now our combined total stress pressure is 53 MPa. It is 4 MPa less than the least principal stress, which does show that mathematically this model does go around and how the lab is now coming to the field and how we can take this new understanding and we can apply it to the field, analyze your pressure response through machine learning AI, learn and dictate off thousands of stages that we've done in the past to make your well better. If we open up our mind and have a new mental model, And I'm not saying this is the end all, but a portion of opening your mind. The naturally fractured reservoir, which is required in rate transient analysis, trilinear flow, you can see it satisfies many reservoir production frac models for non-unique solutions. You just dial up that natural fractured component and that will production match your well. It unfortunately is very difficult to image. And if you were to target this through exotic 3D seismic, AVO practices, things like that, you will reduce your sweet spot. And we're starting to hear less and less of that terminology used in industry. Rather, if we open our mind to a new mental model of bedding plane party, it is present in all unconventional reservoirs as they're deposited in, well, the majority, low energy, distal, marine environments with kerogen in layered orientation. And there are a few exemptions with lacustrine deposits, but again, this is a layered rock system, high level of anisotropy. It exists in all. Can we optimize our type curve if we do understand the trilinear flow model, and can we mitigate risks? And here's an example underneath of the Vaca Muerta in Argentina, the Eagleford in the lower 48, the Montney here in Canada, and the Marcellus on the other side of the lower 48. All of these, anyone can see, are layered anisotropic rock shales. Another example, I'm not sure if you can see this. This is an image log down a typical Montney wellbore here in Canada. I've looked at maybe 10 kilometers of image logs, and they do not look like this. They look like the lower portion of this, which is mostly intact with maybe some wellbore breakouts. They do not look like a rubbleized, fractured mess, which we see in the upper example. So if we're to take these learnings, what does it matter? If we say now, let's take advantage of our layered anisotropy. Let's get more complexity in our frac. Rather than targeting zone A, which has maybe a sandwich with a couple layers of tomato, let's take a Big Mac with 20 layers of complexity, and let's target this. By doing this, what we're seeing now with our AI machine learning algorithms applied to targeting facies-specific benches, and even benches that are conventionally targeted in unconventional systems, we're actually seeing a shallowing of the B value. And that shallowing of the B value goes out to higher EURs, more sustained cash flow, and higher recovery factors from your reservoir. When I'm to look at case study examples, we could probably go into these for another 30 minutes of case studies, but very, very high level. Here's an example of the Eagleford. You can see the Eagleford here. We were with a company in the Eagleford, and we increased their production by 21%. So 21% in the Eagleford. You can see here's a shear frac pad. These are all other offset operators. And we actually had a sampling against 440 offset wells versus the 20-something that shear frac was on. Those outperform all other operators in this normalized to lateral length, tonnage, and completion specs by 20-something percent. You can see in the Montney formation, I believe on this one, we're achieving 18% uptick. And this is in Canada, in the Wembley area. This is the high liquids. And you can see again, cum production, shear frac wells, by taking this lab learnings, applying it to the field, and actually keeping ourselves accountable with real-time production after the fact, we can see here we have an uptick. There's another example in the Midland Basin here. I believe we were 19%, and in the Delaware Basin, again, much higher. So these are repeatable results, and these are actual well results from operators. These are not from public data. This is from actual operators going back through after 90 days, comparing their completion against what we do. We always hold ourselves accountable. We always measure ourselves in the value and barrels added to your company. And I hope this talk opens your mind a little bit to maybe there's a different way of thinking about how fractures happen underground. Any questions? You can gladly reach me. Please reach out to ShearFrac, and we will gladly answer any questions you may have. And thank you for your time, folks.